the kilograms would cancel off, and you're going to have a meter squared over second squared. And then, of course, the final step is to take the square root. And so if you take the square roots of all this, the meter squared becomes meter, and the second squared becomes second. And sure enough, our unit analysis works well, because remember, and this might be one of the hardest calculations we've done so far this semester, is to say that, hey, I'm asking a question about speed. I know the answer should be in meters per second. Do my units work out right? Because if they don't, I know I did it wrong. And if they do work out right, at least I think I can say that, okay, I'm heading in the right direction. So sure enough, I got meters per second. And so that's why I put that here. Now, I'll try this calculation too. Let me do this. I already multiplied those two together, so let me just copy that down. Let me then divide that by, and I've got to add two things together, 6.37 times 10 to the 6 plus 400, 1, 2, 3,000, close parentheses, hit enter, and take the square root of all of that, and I get a speed of 7,676 meters per second. And so, as I said, it is a little slower, not much, and again, we're not very high. Okay? And so I'll say it again. Be on the lookout, because I'd say I'm really kind of explained the whole chapter, although there's some little subtleties I want you to see. But all I've done here in this problem is take the universal gravitational law and together with some past materials, and I can ask then what speed is it. And of course I asked for the International Space Station going around the Earth, but I'm hoping you can see this could have been a question that says how fast is, say, the moon going around the Earth, or how fast is Venus going around the sun. And then I would be, having the two objects would be Venus and the sun. Of course, the mass of Venus would cancel off, so I wouldn't need the mass of Venus, but I would be able to then come over here and say, okay, I need the mass of the sun in order to finish the calculation. And in fact, why don't I do this? What if I were to ask this a little bit further and say, how much time is it going to take then for the astronauts to make one complete orbit around the Earth? So as they go around, you might say as they watch a sunrise and a sunset, so they go all the way around the Earth, how long would it take? And I bring that one up because, again, we learned back in chapter 2 that if something is moving at a constant speed, it would be distance divided by time. Or maybe I should put it this way, that we learned that distance divided by time is the average speed. But we also learned, if you remember this diagram, I used a baseball in the diagram and said if the object is moving then to the right with some velocity v, and you apply a force that is perpendicular to it, that force makes it turn. And of course, a force in the direction it's moving makes it go faster, just to complete the diagram. And a force that is the opposite direction it is moving makes it go slower. But you see what I am doing right now when I'm talking about a circular orbit here is as I go around a circular orbit, the tug of gravity is perpendicular to the direction it's moving. And so the tug of gravity doesn't make it go faster or slower. It's this part of the diagram. The tug of gravity just makes it change directions. And so the International Space Station is being pulled by the gravitational force of the Earth, but it's not like dropping a ball where it goes faster and faster and faster. This tug of gravity is making it turn. The moon the same way. The moon doesn't end up going faster and faster and faster. It just turns it. And so I have a turning going on. Now the reason I say all that is because, again, the average speed is really just the speed. If we come back to this International Space Station, we got the speed, this 7,676 meters per second. This is the speed. And it doesn't go faster, it doesn't go slower. Is it under the force of gravity? Yes. Is it accelerating? Yes. But that force of gravity, that acceleration, is changing direction. It is not changing its magnitude of its speed. It's not going faster, it's not going slower. And so again, I hope you're seeing in my thinking here, what I'm doing is just taking this new piece of information and applying the past chapters to it. And where that can be very useful then is if I rearrange this equation like we did back in chapter 2 and said time would be distance divided by velocity, I might be able to answer this question: how much time does it take for the International Space Station to go all the way around the Earth? And so to answer that, I would need to know, well, in the top, what is the distance that the International Space Station travels? And in the bottom, what is the velocity? And the velocity I just did, so that is the 7,676 meters per second. I think that's what I saw. Let me double check. Yeah. And so that's the velocity of the International Space Station. The distance is really going to take you back to your geometry class, or maybe even an algebra class, because it's going in a circle. Of course, the distance around a circle we call the circumference. What is the equation for the circumference of a circle? And 2 pi r is that equation, where in this case r is the radius of the Earth and the altitude of the International Space Station. And so if I grab my calculator here again and go, all right, what is the distance that the International Space Station travels? And so 6.37 million, add to that 400, 123,000. So that's the distance. And then multiplied by a 2 and multiplied by a pi. This comes out to be 4.25 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. And then divided by 7,676 meters per second. So divided by 76. And so this comes out to be 5,541. And let's just check our units. This is that compound fraction. And so I would have meter over 1, and then flip this, makes a second over a meter. The meters cancel off, and we're left with seconds. So I'm asking for time, and I would expect then the units to come out to be seconds, and they did. So there's my unit analysis. Good. Makes me feel like I'm doing things right. And it might be more useful to divide that number by 60 to figure out what it is in minutes, and it looks like it's 92.4 minutes. And remember, 90 minutes is an hour and a half. So this is a hair more than an hour and a half. Let me just call it an hour and a half. And so these astronauts, if you will, as they go around, they'll see a sunrise and a sunset every hour and a half. Okay? And so there's the answer to all that. Well, I better leave this alone, but I think what you're getting, at least I hope what you're getting, is we could take this new piece of information, this right here. Simple calculations would be just what is the force. But once we know the force, if we tie it together with the other chapters, chapters 2, 3, and 4, and again, motion in space, Newton's third law, chapter 3, or the description of motion in chapter 2, we could start asking more about these satellites as they go around, or anything that's going around a planet. Like I said, Venus going around the sun would be a good description of it. Well, I better wrap up this chapter. There is one more thing to say about this. There's not numbers here, but it's more of conceptual, and it has to do with the tides, because the force of gravity is responsible for our tides. But the tides are an interesting effect of gravity that is, well, let me just say interesting. Maybe I should say misunderstood. There is a common misunderstanding about the tides and, you know, why we have them. And let me explain. Because if you take the Earth, and so let me draw the Earth, and maybe in a simple model, I'll do this. Let's just say that the Earth was this perfectly round ball, so there's no continents. And then on top of the Earth, there is this big puddle of water. And so imagine an Earth with no continents for a moment. It is just a solid ball, and then on the surface of the solid ball is this liquid water. And if the Earth was all by itself, the water would spread out equally, and that's what this dotted line is supposed to be. But let's say then the Earth is not by itself. So you put an object near the Earth. And the two objects I want to talk about are the sun and the Earth. So I won't at this point say whether this is the sun or the Earth. I will just say it is another object. What will that object do? And I think you already know that this would be result in tides. But why? And this object here, either the sun or the Earth, would put a gravitational pull, and it would pull the whole Earth towards it. Okay, so let me redraw that. Let me say, and I'll just go right below. In fact, maybe I'll even do a difference color here to kind of show that, okay, if this is where it was before the Earth was there, I'm sorry, why did I put Earth there? I meant to put moon. All right, so without saying whether it is the sun or the moon, either object is going to pull. And so let me first just maybe draw a vertical line and point out then, and I'll exaggerate, that the Earth gets pulled towards that other object, whether it be the sun or the moon. But here's the part about tides that I want to emphasize, and your author does too, is if everything got pulled equally, then you would just have the Earth a little closer to the sun or the moon. And then all the water that's on the Earth would also be a little bit closer. But for somebody on the Earth, they would still see the water as uniformly distributed, and that's not a tide. A tide is where some of the water is higher than the other. And the reason that this is a poor model, so I will do a better picture still. And so here the Earth gets pulled towards the sun or the moon. But you need to understand this important question right here. That the force of gravity does change a little bit with distance. And the Earth's center is here. But the water that is closest to either the sun or the moon is a little bit closer. And because of that, the tug on the water is a little bit more than the tug of the earth. And so the water, if I can exaggerate, gets pulled out more than the earth itself. And so there is a growth, if you will. There's a bulge. And this, the water is deep. And it pulled it away from the sides, so the water is shallow. And so some parts of the earth we have deep water, and other parts we have shallow water. That's what a tide is. And so this really is then a tide. And what I want to emphasize is the tide was created not because of the force of gravity, but because of the differential of the force of gravity. That's why from a physicist's point of view, there's an important, extremely important description of why there is tides. Tides are not caused from the force of gravity. They are caused from the differential in the force of gravity. The fact that the part of the earth closer to the sun or the moon gets pulled more than the earth itself is how you get a bulge. In fact, I've got a kind of a silly example here with this bungee cord. If I take this bungee cord and you look at the bungee cord, you'll see a piece of tape I put on here that's yellow in color, and then a center one that's red, and another one that is green. And if all I did was take this whole bungee cord and push it to my right, then the yellow, red, and green pieces of tape are still the same distance apart. There is no bulge to them. It doesn't matter how hard I push it. I could push it a little bit or I could push it a lot. It is not the amount of force. It is the differential in force. To get these colors to separate, if I take my right hand and pull it to the right and my left hand and pull it to the left, now they separate. Now they get a little further apart. And so I would say what separates them is not how much force I put on them, but the differential force between my left hand and my right hand. If my left and my right hand both push equally to the left, or my right, or to my left, your right, as long as my left and right hand push the same, there's no separation between these. It is not the amount of force that separates these two. It is the differential in force. Now, most people, when they look at a bungee cord, they say, oh, yeah, you're going to pull with your right hand to the right and your left hand to the left. That will stretch it. But I would even say, if I take my right hand and go to the right, and I take my left hand and I go to the right, it will stretch if I pull more with my right hand than my left hand. And so if I do this, it stretches. And so this is a way of me trying to emphasize, maybe overly emphasize. And I'll say it again, the tides are not created by the amount of force. They are created by the differential in force. That's why we have the sun and the moon. They both contribute. And as you are going to see here in a second, well, I'll just say it now, that the moon actually contributes more to our tides than the sun. The moon does not pull harder than the sun. I think that's obvious if you ask, well, which pulls harder on us, the moon or the sun? Well, you can see that we orbit the sun. We are influenced by the sun. The amount of force on the earth from the sun is way more than the amount on the moon. But yet the tides are more determined by the moon than the sun. Because I'll say it again, the tides are not determined by the amount of force. They are determined by the differential in the force. Well, I'll keep going with this, because watch this too. The backside of the earth, and what I mean by the backside is the side away from either the sun or the moon, that too would be pulled, but it would not be pulled as much. It would make another bulge. Not because the water got pulled this way. It's really that the earth got pulled to my left more than the water on the backside got pulled to my left. Everything got pulled to the left. And going back to this bungee cord, this is what I mean when I say the best way to illustrate the tides is to emphasize the tides are not determined by the amount of force. If the amount of force was equal from my left hand and my right hand, and I move them to my right, your left, like that, there's no stretching of the object. The way you get stretching is if my right hand pulls more than my left hand. And again, they don't have to be opposite in direction, although that works. They can be in the same direction. And that's what we have with our tides. Where my right hand and my left hand are actually pulling the same direction, but my right hand is pulling more than my left hand. And so it stretches out, it elongates. And the stuff in the middle gets pulled away from the stuff in the back. And the stuff in the front gets pulled away from the middle. And so you get these bulges. And so remember, the earth, of course, is spinning. So in a 24-hour period, what will happen is, let's say we're right here. This would be, say, Santa Barbara. We would be in the place where the water is low. We would call this low tide. To us, it would look like the water is way out and the water level is low. But with 6 hours later, this spins around, we would get into high tide. And then 6 hours later, we would get into a low tide. And then 6 hours later, we would get into a second high tide. And then back where we started. And so to understand why there are two bulges is really important to understand that the tides are not determined by the force. They are determined by the differential in force. So maybe I said that way too many times, but I just want to keep emphasizing it's the differential. So that is our answer then why the moon has a bigger effect on our tides than the sun. Even though the sun pulls on the earth with a larger force than the moon. The moon has a larger differential. Why? Now it's back to here. The moon, so let me draw a new set of pictures here. And so if here's the earth, the moon is roughly 240,000 miles, well, let me use miles away. But the sun is 93 million miles away. The Earth's diameter is roughly 8,000 miles. So when you look at the front of the earth and the back of the earth, you would have to take this distance and subtract 4,000 or add 4,000. And when you subtract or add 4,000 from 240,000, that is a bigger effect than if you go plus or minus 4,000 out of 93 million. And so the differential, and so we call these tidal forces. It's not the amount of force, but it is the difference between the front and the back of the earth. And so the differential from the moon, because it is closer, has a bigger effect than the differential from the sun. And so I probably shouldn't say it more times, but I just can't emphasize it enough. People get the wrong understanding that the tides are caused by gravity. And in part they are, but it's not the force of gravity. It is not the magnitude of the gravitational force. As I said, if that was true, the sun would have a bigger effect on our tides than the moon. But it's the differential, and because of that, the moon has a bigger effect. And so an interesting consequence can happen here depending on how the sun and the moon line up. And so if we get something like this, and so I'll come over here and put the Earth again here, so here's the Earth. And if the moon is here, in the same line as the sun, we would, by the way, call this a new moon, because from planet Earth we would look out and the lighted side of the moon would be that way, and we would only have the dark side. So we couldn't see the moon. That's why they call it a new moon. It like disappeared and it's going to show up again. So, and not only are we looking at the dark side of it, but we would to see it, we would have to be looking in the daylight. And it's just, you just don't see the moon. But I would draw it like this. I would say the moon then would cause a bulge. And then on top of that, the sun would create a bulge. And they would be working together. And the overall effect is a very large bulge. And so this is when you have your high tides and your low tides. Because if you have the high tides, you are drawing a lot of water then, so you also have your low tides. And so in our area, if we call these our king tides, this could be a part in the monthly cycle here where you have your big tides. And so maybe high tide is 8 feet above sea level and maybe low tide is 1 foot below sea level. I will point out then that a little surprising until you remember it has to do with the differential. 2 weeks after the new moon, we have a full moon. In a full moon, the moon has moved to the other side of the Earth, and so the lighted side is pointing straight back at the Earth. And so somebody on Earth could see it, and it would be at nighttime. And so at nighttime they would look up and they would see the whole thing illuminated. And so this full moon would, again, you would get a set of bulges from the differential from the moon, and then you would get a set of bulges from the sun. And again, they're acting together. And so during a new moon and also during a full moon, you get these really, really high tides, which also correspond to really, really low tides. And so there's about a 2-week period between these sets of really high tides and really low tides. In between that, though, you would have a picture that would look like this. You would have let me dry this here. If you put the Earth here, and I'll put the sun over here again, and now the moon is, say, right here, and so the lighted side is back there. We call this the first quarter. Makes sense, right? It's a quarter of the way around. And so it would be about 1 week. So the new moon would have been here, and so a week later we would have been right here. Of course, what that means then is the lighted side from Earth, when you look up, you don't see the whole moon illuminated. You just see half of it illuminated. It's a quarter of the cycle, so it's called a quarter moon. It also means that you would see it up in the sky anytime in the afternoon. And so as we are spinning around on the Earth in the afternoon, we would see it, even though it's daylight. And then, of course, after sunset, when we got on this side, and so we're on the dark side of the Earth at this point as we're spinning around, we would still be able to see the moon. And so we can see this at night until about midnight. And so from sunset to midnight, we got a good view of this moon. But after midnight, we would be well over here, and we wouldn't be able to see the moon anymore. What I'm getting at, though, in terms of tides, is you would get then a bulge, and see if I can show these maybe competing with each other. You would get a bulge from the effect of the moon that would look like this. And then fighting you, not that you would have both of these at the same time, you get the combination of the two. You would get a bulge from the sun. And again, I hope my drawing doesn't confuse you. I'm not trying to say there would be 4 high tides here. I'm trying to say then the result of this would be the combination of the two. And since the moon has a little bit more of a dominance compared to the sun, the final result might just be something like that. And so your high tide is not very high, which then also means your low tide is not very low. And so after we have this new moon where we had these really high tides and low tides, a week later we're in this position and our high tide is only like 4 feet and our low tide is only like 2 feet. And so there's really very little movement to the water. And so one weekend you're out at the beach and you notice a dramatic change in the water line. And then the next weekend you're out at the beach and there's very little movement to the water line. And as I said, a week later we'll be over here in a full moon. And I won't bother to draw a second picture. I think you're getting the idea that this argument would be the same as when the moon is over here in the third quarter. You would basically get the same thing as the moon is in the first quarter. So the effect of our tides in the first and the third quarter is really the same, just like the effect of a new moon and a full moon are the same. And anyways, and this just keeps going around. Now I must say, there's other complexities to this, which maybe I'll stay away from. But if this was a oceanography class or an astronomy class, maybe I should go further with this. But you could imagine that the continents, so as it turns, and you might think of this as the landmass moving into the bulges would shift and push the water. You can get some really interesting effects. And so the tides in, say, Santa Barbara could be very different than, say, Monterey or the East Coast versus the West Coast. Also, another fun fact here is I've only drawn things in 2 dimensions. But 3 dimensions really are kind of neat because now you have the sun here, but the moon is here, but the moon is off at an angle, and so it goes up and down, crossing the plane, and so it's either with them or above them or below them. Plus, the Earth is tilted and it goes through, and so as we rotate, sometimes we in Santa Barbara might go right through the center of the big bulge, and then on the other side, the big bulge is over here. Well, here, I'll show you kind of this. If you take the Earth and you tilt it something like this, and if this is the sun over here, when Santa Barbara comes over here, you might be in a direct place where the bulge is, and so you get a high tide. But 12 hours later, because of the tilt of the Earth, the second bulge is over here, but Santa Barbara goes through this part of the bulge, just a fraction. So your second high tide is different. And so if you ever look at your tidal charts, you'll see that the tidal charts are kind of interesting. There is one high tide higher than the other. They don't exactly match, and this simple model doesn't really explain that. You have to have the tilt of the Earth and the 3-dimensional effect for all that. But again, as I said, I probably should leave that alone here. All right, so let's move on. And as I said, the chapter 5, I hope, has come across to you as just one simple new idea, the universal law of gravity. But when you tie that together with the other chapters, it could be really rich in complexity and rich in problems. And that's what you'll see as you do the homework and as you do the test. All right, well, I'm going to take this as an opportunity. It's not quite time for our break yet, but I'm going to take this as a chance to say, let's start chapter 6 here, because what I'm hoping to do in the second lecture here today is to not only wrap up chapter 6, but have quite a bit of time to give you kind of a summary and kind of explain the first test and kind of help you get ready. And I know at this point you probably have a lot of nervousness and anxiety about what's the exam going to look like. And I hope that hour of summary and showing you some of the calculations and maybe even giving you some advice on how to prepare yourself beyond the obvious, which is watch the lecture, read the book, do the homework, do the labs. Those are the obvious ones. But you can even go a step further if you want to be what I'll call extra prepared. Or if doing all the normal things don't really have you prepared, you might be asking, what can I do next? And some of you shot me an email about that, saying, okay, I'm starting to get the hang of this, but I'm still struggling. And by the way, that's probably just fine. That's a normal good sign. Remember, we're still 5 days away from the test, so there's a lot of chance. I would say there's no chance in panicking quite yet. You got 5 days, and that's plenty of time to learn the material. And hopefully you're not behind, so hopefully you're not playing catch up and trying to learn the material. If that's the case, you'll need all 5 days, so you're not in trouble yet. But if you don't get started right away, you will be. All right, well, looking up the clock, I'll take a few more minutes here and just say, what is chapter 6? And chapter 6, the